Hello students, welcome to EPG Pathshala. I am Dr. Dinesh Kalyanasundaram from IIT Delhi. Today we are going to talk on Fourier series. The objective is to understand what is Fourier series and what is a periodic function and how are they related and how to represent a periodic function in the form of series, and that is exactly what is Fourier series, and that's what our objective for today is going to be. Fourier series. We are going to see what is Fourier series, when to use it, and what is the physical significance, and we are going to see that with some solved examples to help you better understand. What is Fourier series, right? So the idea was initially conceptualized by a French mathematician, Joseph Fourier, and he said the crazy idea was, he said any periodic function. What is a periodic function? Which is going to change with respect to time. It has a definite period. It's going to repeat itself. So he's talking about any periodic function can be written as a weighted sum. What is a weighted sum? It's probably some of them are proportional and some of them are not, and they are going to be a proportionality constant, which is going to be called the weight of the particular function. Okay, as a weighted sum of sines and cosines of different frequencies. So we want to give certain frequency more importance, so we are going to give different weightage, and some frequencies we don't want to give them so much weightage, so then we are going to, or importance, so we are going to manage how the how each frequency is going to reflect to represent a particular function, and that's what's going to be the weighted sum of sines of different frequencies. And you may not believe it, and even Lagrange, Laplace, Poisson did not believe that this is the biggest tool, but right now this is the most important tool that they have found in mathematics. This was not translated into English until 1878. Okay, so we are going to see how Fourier transform and Fourier series has been the possibly the greatest tool in engineering. Okay, Fourier series is a convenient representation of a periodic function. Why do we say convenient? So we can just modify according to what we really want to show, and it is easy to modify to represent any function. Now, when I say any function, any periodic function. Okay, it has both sine and cosine terms, and it can the frequency, so that means the sine of omega t, the omega is going to be different, so we are going to multiply it with some constants. Why only sine and cosine terms? Now that's going to be the fundamental question. Why not cotangent, why not secant or cosecant? Okay, the answer is sines and cosines are the most fundamental of any periodic function. It can represent any function in any domain. We can always write it in terms of either sine or cosine or sum of both. Trigonometric functions which have different values for all angles in its one time period. So basically sine and cosine will have all possible combinations of values within 0 to pi. Now we can represent Fourier series as a sum of sinusoidal harmonics. Now what are harmonics? That we are going to see in the next slide, but the graphical representation we are going to see in the next slide, but we are going to see what is the text definition. The text definition is signals or functions obtained from whole number multiples, that means whole number integers of the fundamental frequency. So, and that's exactly what I was talking about. sine the frequency, let's say omega times t. It can be 1 omega, it can be 2 omega, it can be 3 omega. So it's whole number multiples. What is the building block of that? Building block of a common sinusoidal function, you can write it as a times sine of omega x plus psi, or you can say omega t plus psi. What is A? A is the amplitude of the signal. Sine is the way how it is going to sinusoidally change. What is omega x? Omega x is the frequency. Omega is the frequency. X is the variable, or it can be t. What is psi? It is the phase difference. It's going to just shift by phi. If it is minus psi, it is going to shift by some minus psi previously. Then now, what is the next step? Now we have found out the building block of a sinusoidal harmonic. Now we have to add enough of them to get any periodic function or signal f of t you want. What does each control? Each controls the structure of the function. That means you may take a1 sine omega plus psi, then there is a a2 sine omega 2 x plus psi, then there will be a3 sine omega 3t. But now what the psi can be there or cannot be there. Okay. Now course structure. Which one defines the course? Course meaning the bigger, and fine versus a fine structure. So we need to represent a complicated structure in terms of both coarse and fine structures. Right? We can separate any complex structure into a coarse and a fine structure. The coarse structure is actually captured or replicated by lower harmonics, which is lower frequency terms, right? So omega or 2 omega t, they are all lower frequency terms. What is a fine structure? Fine structure will be captured by higher harmonics terms. For example, let's say 20 omega t or 7 omega t, something which is much larger than, let's say, 3 omega. It's generally into the higher harmonics. We are going to see Fourier series as a sum of sinusoidal harmonics. Before we see what is the sum, we need to know how the individual harmonics are going to behave. Okay, so for the same amplitude, okay, and then we are going to assume 2 pi or twice pi, which is 6.3 around. So for one cycle, so that means there's only one cycle. You can see the curve, and there's one crust, top one, and then one trough, which is the bottom one. And this whole one sinusoid is fitted in this 0 to 6.3. Now what is second harmonic? Second harmonic means two cycles are fitted in the same time period. Then you have two complete cycles, two troughs and two crests. And in third harmonic, there are three cycles, and fourth harmonic. How does the harmonics matter, right? That's what is the question. Now let us say we have a function, a square function as shown by the red curve. It has a top one and bottom one separated, so it's at a value of 2 for the time period t by 2. Then for the next time period t by 2, it is at a value 0. Now, how does the sinusoidal harmonics going to help us in formulating the square wave? Okay, now how are we going to do that? Now that's what we're going to see in the next few slides. We are going to see how we can go from one signal to the other. First, we have to actually understand what is the required signal. The required signal, it stays at a value 2 for t by 2. Then there is a discontinuity as shown in the right side figure. Then it falls immediately, sharply to 0. Then it continues again for t by 2. Then it sharply increases So it is not a really natural signal. It is a assumed signal because any system cannot go between value to 0 immediately. Okay, but this is a, let's say for the time period we will just assume. We are going to see how to get that square wave, and let us do by practice. Let us open an Excel sheet, put time t values from 0, 0.1 to 6 separated by 0.1 time interval. So 0.1, 0.2, 0.3, 0.4 up to 6.0. Now calculate sin t. Then calculate what is the value of 1. Okay. Now add 1 plus sin t. What are you going to see? You have a sin t as shown in the left graph. Then 1 constant value. When you add these two, what happens? There is a shift in the right side graph. Right? That is 1 plus sin t. Now taking the learning from the previous slide, we have 1 plus sin t which is shown in the left side. Now let us do a funny thing. Let us add it to 1 over 3 sin 3t. So what happens is this 1 over 3, the amplitude is reduced, and sin t, the number of cycles is increased. Now when you add these two, you will get a graph as shown in the right side. You see, we are somewhere going towards the square wave. We have already got it. So the coarser functions are obtained by the lower frequencies, that is sin t. The finer details are obtained by the higher frequencies, which is the sin 3t. Let us redo the same thing, but let us add a sin 5t. So we have 1 plus sin t as shown in the left side figure, then 1 over 3 sin 3t in the middle figure, and 1 over 5 sin 5t again instead of the middle figure. When you add these three things, you can see the right side graph is becoming more smoother and more finer. And that is the series 1 plus sin t plus going up to 1 over 5 sin t. Now, it is up to the individual how many terms he wants to use, depending on the computational time and energy that a person or the system or computer, whichever is doing, has. Okay, so if you want to exactly go to the square exactly thing, maybe you have to go up to sin 21t or maybe sin 40t. But if you are okay with the so-called representation of the square wave, maybe you can stop with the first 3 terms. So just for the love of experimenting, let us experiment sin 21t2. So we keep on adding the odd terms. Remember, not the even terms. We are adding the odd terms. And then you can see nearly square wave has come. Now what you should go on experiment is, you should experiment adding 1 by 2 sin 2t, all the even terms, and then see what it is going to give you. Because unless you experiment this, you will not understand what is Fourier series, how it can help you to model anything. See, philosophically, this is same as having a dot, right? You can draw any image using a dot. Different sizes of dots, you can actually draw any image. It is the same concept like collage, like some people make picture of any person just by taking newspaper bits, random newspaper bits, and they can paste it in a way that you can make an image or a facial photo of any, maybe a VIP or maybe yourself too. And that is the same thing we are trying to do. They are all forms of Fourier series. Just that we are going to take something and add it with different forms in different functions. So this 1 over 21, 1 over 3, these are called the weights, the weightage that we are going to give. If you are going to change the weightage, again the form is going to be different. So you will have to see how to manipulate the weightage, and you have to see how to manipulate the addition process. Okay, and then you will get any wave. For example, if you can get square wave, literally you can get any wave and you can go from there on. we are going to see another example which is as hard as a square wave. What is the next one which is as hard as a square wave? Which is a triangular sawtooth wave. And many electronics people use this, and you may also have to use it because you will end up using electronics mostly in bio related stuff. Okay, now how can we approximate? Now can you see the image on the right side where you can see the red graph, red line, which is 1 by 2 minus sin t. Okay, so what happens with 1 by 2 minus sin t? You get a graph. The 1 by 2 is just shifting in space, and you will get a red graph. Now next go to the next term, the blue broken lines, 1 by 2 minus sin t plus 1 by 2 sin 2t. Again, you always see the weightage is always 1 by the constant times what you are multiplying, sine into sine of the same constant times time. Okay, this is a very usual practice, and then maybe you can follow it, it get to the result very quickly, or you can use different weights, but that's not going to change. If you use approximate weights, you get to the solution quickly. If you use different weights, you will get to the solution, but maybe a little longer. That's okay. And let us use the next term, which is the black solid line. So black solid line, you can see which is 1 by 2 minus whatever the whole terms, where you have 1 by 2 sin 2t, 1 by 3 sin 3t, 1 by 5 sin t. Then you can see it is depicting the near sawtooth curve. So if you add more terms, probably you will end up getting what you want. We are going to see another, maybe not so difficult, but we are just going to see another example, which is a half sine wave. And many times when you use a DC rectifier, maybe you will get this kind of half sine wave in the first rectification. So what we are going to do is we are going to try this number as shown in the red line, 1 plus 1.7 1.57 sin t. Find out what is 1.57 in terms of. So we will get initially sine graph, which is, you can see it is elevated, which means you have shifted the curve. Can you notice that? Because you added the number 1. So it has done a DC shift, which means the whole curve has shifted upwards. Now when you do the see the blue curve, which is the double dotted line, probably you are not able to see it clearly. It's very slightly visible, hiding behind the black line. And then you can see it starts, following the half sine curve. Then when you do more number of terms, okay, now you have sin t, then you have cos 2t, then you have cos 4t and 6t, then you can actually capture it much more. Okay, so in these ways you can actually capture what is your area of interest. Here what you should notice is there is a sine term and there is a cos term. So previously we were only seeing one type of terms, now we can see two types of terms. So more complicated stuff is what we can capture. Fourier series mathematical representation. The Fourier series can be written as f of x, which is the function, can be written as a0 by 2, that is the initial constant. Then we can write the repeating functions, which is sum of n goes from 1 to infinity. So you can write as many terms as you want to represent any function f of x. And for the first term is going to have a1 times cos 2 pi x divided by time period plus bn sine or b1 sine 2 pi x by time t. And then the second term is going to be a2 cos, so you have to replace n as 2, and then you will get the values. So you can write several cos and sine functions and add it up together and represent a function f of x in terms of just cos and sine, and this can be any function, and that's the beauty of this. So any complicated function you can represent sine and cos, then you can differentiate, and that is what is we are going towards. The coefficients a0 and an can be calculated by the formula as given. The complex form. The complex form can be written as follows. F of t is minus infinity to infinity Cn e power jn omega naught t, and here you should notice that the differences between the previous term and this one is there the n started from 1 to infinity and here it is minus infinity to infinity, and the constant value Cn can be found by the formula shown here. Fourier series convergence condition. The first condition is the function f of t with time period t should be integrable within its time period capital T. So that means minus, if you integrate the function f of t with respect to dt and apply the limits between minus t by 2 to plus t by 2, then that should be a finite value, that should be less than infinity. The function f of t, the condition number 2, the function f of t should be a single valued piecewise continuous. What is a piecewise continuous? It must have finite or few number of jump discontinuities. Then it is called piecewise continuous, and also piecewise monotonic. What is a monotonic? Must have finite number of maxima and minima. So you can't have a function which is like multiple times reaching maxima and minima. That is not piecewise monotonic. Okay. Then if f of t follows the above conditions, then the Fourier series of f of t will converge to f of t. Otherwise, the Fourier series will not converge. We are going to see the difference between even function versus odd functions. Even function. A function is even when f of minus t is equal to f of t. That means it is the same function on both sides of the origin. Then it is supposed to be even. For example, a cos function. You see the both sides of the cos function, cos of minus t and cos of t are same, and f of t squared. If you put t as minus something or plus something, both values are going to be squared, so the negative sign is gone, and you can see the values also, whether the x value or the t value is positive or negative. The y value will always be positive and will be equal, and the same thing applies to t power 4. Odd function. What is odd function? F of minus t is actually minus of the function of t. That means if you replace the time in the reverse direction, then the value also gets reversed. It's not the same value. So f of sine t is a good function. If you change this value, then the value of sine, if you change the time t to minus t, then the value will also become minus. Same thing with the f of t, same thing with f of t cube. So all the odd powers will always be odd functions. Even function versus odd functions. Properties of even and odd functions. First we will look at addition. The sum of two even functions is even, the sum of two odd functions is odd. The sum of an even and odd function is neither even or odd, so unless one function is 0. Multiplication. The product of two even functions is an even function. The product of two odd functions is an even function. The product of an even and an odd function is an odd function. We are going to see some solved examples for Fourier series. We are going to see two examples. Let us find the Fourier series for the following functions. F of x is equal to minus x, and that x value for minus x will be only applicable in the range minus pi to 0, and the value is x between 0 to pi, and f of x plus 2 pi is equal to f of x. Similarly, we are going to see another function as described here. Let us see the solution. Before we see the solution, let us plot it. So you can see the plot as shown in the image. Okay, so now it's like a triangular wave, and you can see, and the fundamental range is the period pi, 2 pi, and it repeats itself. So let us first find the value a naught, because that is what we should do before writing the function. in terms of Fourier series. Okay, so we have purposefully not taken a simple functions, we have taken a complicated function so that you can better understand that once you do this, you can actually do what you can do where other functions are, you can probably do it much faster and easier. Okay, so a naught is equal to 1 by t times minus t to t by 2 f of x dx. Okay, so then when you integrate, then it becomes a naught is equal to 1 by 2 pi minus pi to pi f of x dx. Okay, so similarly we are going to solve all these things, and we are going to find the coefficients of various numbers, and then we are going to solve it. A naught is equal to 1 over 2 pi minus pi to pi integration f of x dx. Okay, so that is equal to 1 over pi 0 to pi f of x dx, because the time period is half, so the time period is double, so the 2 gets cancelled out, and so when you integrate, a naught is equal to 1 over 2 pi 0 to pi x dx, because our function is x, so then you will get a naught is equal to pi by 2 finally. If for finding an, because the value is different for an as well as a naught, now we are going to again try this one, an 2 over t minus t by 2 to t by 2 f of x cos 2 n pi x over t dx. Now when you again solve this to put f of x as x and then cos nx dx, then you know how to solve it, because again integration by parts. Okay, that is something you will have to try it out, but I can tell you the end result. It's going to be 2 over pi n squared minus 1 to the power of n minus 1 whole brackets. Similarly, we can find the value of bn. Okay, 2 over t integrated between minus t by 2 to t over 2 f of x sine 2 pi nx over t dx. Then since sine is an odd function, f of x and f of x is an even function, the product of the functions is odd. Okay, that means what is odd function meaning? The sum is 0, because f of t, the next term will be minus t, then when you keep on adding them, it is going to be 0. So we can easily write bn as equal to 0. So we can put back the coefficients back into the Fourier series, and then the whole series is going to look like f of x is equal to pi over 2 minus 4 by pi cos of x minus 4 by 9 pi cos 3x, and so on. Let us see another example where the function is 0 between 0 to 1, and the function is x between 1 to 2, and f of x plus 2 is equal to f of x. That means it is going to get repeated after the period of 2, is just going to get repeated. Now let us find a naught, and you know it is just integral between 0 to 2 f of x dx, and you can separate out the terms because we are going to integrate between the time period. So you will get a naught as 3 by 2, and we will go to the next slide to see what are the values of other functions. What we are going to do is find the value of an, and an is going to be similarly written f of x cos nx integrated 0 to 2 dx, and again it can be split from 0 to 1 and 1 to 2 because the value is different. When you multiply by 0, then the whole function is 0, so that is not valid. So then we are going to just see cos n pi x dx integrated between 1 to 2, and then you can take similar integral by parts, and you know whenever there's a cos or sine how you have to do it. You'll have to look up certain books and then see how we can do it. Even in the Laplace we have done a similar one. You can refer to the Laplace videos too. So if you take, then an is equal to become 1 minus cos n pi divided by n squared pi squared, and the value of n goes from 1, 2, 3 up to infinity. The value of Bn is calculated similarly as we calculated in the previous slides, and we are going to see a similar effect, and just that the values are slightly changed, and we get finally Bn is equal to minus 2 divided by n pi plus cos n pi divided by n pi, which basically is minus of 2 minus of minus 1 power n divided by n pi. Here n is equal to 1, 2, 3 and so on up to infinity. So the entire solution of the function is just going to be f of x is equal to 3 over 4, and then you have 2 by pi squared cos pi x plus 1 by 3 squared cos 3 pi x plus 1 by 5 squared cos 5x, and minus 1 by pi 3 over 1 sin pi x plus 1 by 2 sin 2 pi x, and so on. So students, let us summarize what we have learned in this module. What is Fourier series? It is a representation of any periodic function. How? It represents in terms of sine and cosine. Why it is useful? It represents the frequency component present in the function in discrete form. How accurate it is? Add more and more harmonics of sine and cosine to get more accurate function. So it just depends on how long you want to compute. Thank you.